will resume next January. We have a great lineup of presentations. Today, our final forum, indeed the climax of the whole program that we've been working towards all semester, will be given by Amanda Taylor Lipnicki, Associate Professor of Mathematics. The topic is Crocheting and Mathematics. The title of the talk is Soft Calculus. So thank you, Amanda, and take it away.
Thank you, Emrys, and thank you all for being here. It's funny, Mari Hammond, you have almost the exact same name as one of my best friends from college. So just seeing your name on the screen, I feel supported. I'm like, yes. Today we'll discuss research that is at the intersection of math, art, and programming, as well as education. This is joint work with Megan Martinez of Ithaca College. Can you all see my my cursor on the screen?
Yes.
You do see a cursor moving around? Okay, thank you. Good to know. The slides that I'll be using today are primarily due to Megan, as well with some changes and additions from me. We will focus on crochet, but our results apply to knitting as well. And a bit about crochet and what it is. It's a fiber art which creates fabric by interlocking loops of yarn using a hook. Here is a picture of some fabric. A bit of the anatomy of the stitches is displayed too. You can see that they're counted here. There's one for each V. And there's also a picture of the hook that is used to interlock the loops of yarn to create the fabric. Crochet can be used to create a variety of structures. You can make a baby sweater. You can make little amigurumi objects such as this tiny pug and this lion, as well as many other fun arts. And also mathematical structures like the Lorentz manifold featured here, which was shown in the, sorry, I'm losing track of my cursor, which was shown in the American Mathematical Society's outreach program, and was created by mathematicians to better understand Lorentz manifolds, which are solutions to some differential equations that are otherwise kind of difficult to understand. Now, what is mathematical crochet and knitting? It is using crochet or knit to model mathematical phenomena like the Lorentz manifold you saw before. An early example is Dinah Tamina's hyperbolic planes. Here's a picture of Dinah Tamina surrounded in a bunch of her hyperbolic planes that are on display as an art exhibit. She is a Latvian by birth, and she was a professor at Cornell University prior to retiring. I actually took an undergraduate course in Euclidean and non-Euclidean geometry, which used a book that was co-authored by Dinah Tamina and included a crochet pattern for a hyperbolic plane, and I made one. That was the first time I crocheted. I was primarily still a knitter, but I became more interested in crochet because for people who have not done any fiber art, it's sometimes more approachable, particularly if you're knitting in or making fabric in a circle. Because
Amanda, we're not seeing the slides change.
Oh, yes. Yes, it should be on a slide about what is mathematical crochet.
But when we're seeing what is crochet and pictures of the little sweater and things like that.
Oh, okay. Let me try again. Do you see a different slide now?
No.
Thanks. So here now is truly a picture of Dinah Tamina. She is not a lion or a little tiny crocheted pug. She is indeed a Latvian mathematician, and she, her husband David Henderson was also a mathematician at Cornell University, since retired, and she found that mathematicians were using these inadequate models that you couldn't really work with, that were very fragile. And she made these beautiful hyperbolic models so that you could have something for years to come and something tactile to understand hyperbolic geometry. She was featured when I was an undergraduate in Science Magazine and a host of other popular publications as people became more and more aware of her work. And she inspired many, myself included. A bit about hyperbolic planes. Can you see my new slide now?
Yes.
Thank you. A bit about hyperbolic planes because they are fascinating in their own right. A hyperbolic plane is a surface of constant negative curvature, and negative curvature arises from fitting too much material into a small space. So an example of where that arises in real life is curly leaf kale, like the edges, the way they curl, that is hyperbolic in nature, coral reefs, and even sea slugs. Pictured here are some of my students in a geometry class putting together a hyperbolic model, which is created by taking a tessellation that of a flat plane, which features 6 equilateral triangles around each point, and instead cramming a 7th in there. And you can imagine if you cram a 7th triangle in, that it's going to make the surface curve and bend, and that actually mimics hyperbolic geometry. They spent all this time creating these paper models with tape and scissors and all of these little triangles, and then decided we're going to make a bigger model by fitting our 2 pieces together. So this is what they're doing in this photo. And as you can imagine, these are very fragile and you can't really work with them or necessarily keep them nice for a very long period of time. So what Dinah Tamina did with her crocheted hyperbolic models was revolutionary. Okay. All right, so my inspiration to knit and crochet came from, of course, I was in a knit club in undergrad. That's where I learned. Actually, one of the librarians taught me how to knit because she was the faculty advisor to our knitting club. And I didn't learn to crochet, gosh, really well until I started this research project and decided to first base it in crochet, but we're also doing knitting now as well. As far as mathematical modeling, I became interested in modeling quadric surfaces because they are a part of Calculus 3 when we teach Calculus 3. And much like pre-calculus, when a student learns about 2-dimensional graphs such as a line, a parabola, an ellipse, hyperbola, students in Calculus 3 learn about 3-dimensional graphs such as the quadric surfaces pictured here, the ellipsoid, elliptic paraboloid, hyperbolic paraboloid, 1 and 2 sheet hyperboloid, and an elliptic cone, or as we colloquially enjoy calling them, an egg, a bowl, a Pringle or a saddle, a double bowl, a stretched Chinese finger trap, and a double cone. These surfaces and why their equations look the way they do provide a wealth of examples for students to think about and understand more about 3-dimensional shapes and graphs. Using these examples, students develop 3-dimensional thinking, expanding their abilities to problem solve on many levels, including modeling, art, and mathematical problems with multiple variables. I wanted to create models and patterns that could be used by professors and students for the purposes of having tactile examples of the quadric surfaces, as well as for the fun of learning about the art of pattern making for myself. So our goal now is to take these models or take these graphs, which are smooth surfaces in most places anyway. They're these nice graphs of these surfaces and then discretize them into a series of rows and stitches so that we can create a pattern out of them. Now a bit about crochet. Can you see my next slide now?
Yes.
Okay, a bit about crochet and how it works to help prepare us for pattern making. To create a single crochet stitch, say you already have some fabric, You insert your hook and wrap through a stitch, wrap the yarn over your hook and use the end of the hook to hold that yarn and pull it through. Now, then you will have 2 loops on your hook from the new one that you pulled through. And you will pull the yarn over the hook again and pull it through these 2 loops. And that has the effect of creating another stitch on the current row. This is called a single crochet stitch. Now our patterns will utilize only the single crochet stitch and something called a single crochet increase and a single crochet decrease, or single crochet 2 together. Single crochet increase just means that you essentially do 2 single crochet stitches in 1 stitch. See how there are 2 V's here? This has the effect of increasing the number of stitches on a row by 1 when you include one of these. The single crochet decrease in effect ties together 2 different stitches by going through each of them and yarning over and pulling the yarn through in sequence. And then once you have 3 loops on the hook, yarn over and pull the yarn through all 3 so that you have these 2 stitches tied together. You end up with 2 V's above a single stitch on the current row. So this has the effect of decreasing the number of stitches on the current row by 1. Now, we will talk about creating models using crochet by focusing on a particular example that illustrates really nicely how our pattern making ended up working and how we developed an algorithm for it. So let's take the ellipsoid with equation x squared over 3 squared plus y squared over 2 squared plus z squared over 2 squared is 1. Its graph is pictured here, and here's a lovely drawing with the idea of discretizing the ellipse into a series of rows indicated by the drawn circles here. Cross sections of this ellipse, again, are circles as pictured. And think of each of these circles as a row in our crochet pattern. Our task is then to crochet the series of circles, 1 for every row, but we need to know how many rows and how many stitches should be in each of these rows. Suppose we decide to create 1 row for each half a unit in the horizontal or X direction of this ellipsoid. That we then calculate for every half a unit the circumference of each of these circles, or 2 pi r, where the radius is determined by this equation here of the ellipsoid. Unfortunately, if you look at all of the stitches here, there are some jumps, and it's not actually the most accurate model to create this ellipsoid. So how can we fix this problem? One issue to address is gauge. Every knitter or crocheter has a unique gauge, which depends on the size of the hook they're using, because some hooks are wider and some are smaller. And also the size of the yarn and just how they as an individual knit or crochet. So these numbers are different for everybody. But suppose we crochet a 4x4 square and using our certain size of hook and given yarn, we see there are 22 stitches in 4 inches across and 25 rows going vertically in 4 inches. So we're going to take this as what is called our gauge, which again depends on a given hook size, a given yarn, and the individual crocheter or knitter. So suppose we're setting a row to occur every half a unit. Then in gauge terms, 4 inches per 25 rows will give us 0.16 inches for every single row. The total width of this ellipse will then be, since we have 6 units across in the horizontal direction, 3 plus 3. And we're doing a row every half an inch. That'd be 12 rows times 0.16 inches per row equals 1.92 inches. So just a little bit of conversion factors here. So the total width of the ellipse will be 1.92 inches. And we're also saying the following is our scale. 0.32 inches is 1 unit horizontally in the X direction due to the total ending up being 1.92 inches. So a pretty small model, pretty small scale model, but in some ways this is nice because it also helps the fabric keep its shape better. Now, this is, so we take into account the crocheter's gauge in each circle we made to create the ellipse. We now have a way to take into account the gauge. If we have 2 pi r units around the ellipse, then we can multiply by the number of inches per unit and the number of stitches per inch to get a more accurate number of stitches based on our individual crocheters' hand, how they crochet the material and the hook. But notice there are these large jumps at the ends, and it's quite different from what we had before. It jumped from like 7 to 0 or 6 to 0, and now it's going from 12 to 0. So the crocheter's gauge makes a huge difference in how many stitches there will be. And the beginning and end represent starting from -3 and going to 3 respectively, as indicated by the X values. Now, this is where ArcLength comes in handy because that jump from 12 to 0 stitches is huge. And you can imagine that if you joined all those 12 stitches together, you wouldn't get a very nice smooth shape at the ends of the ellipsoid. What happens at the end of the ellipse is that there's more material than in the middle because the material curves. This means we should divide it into more rows near the ends of the ellipse. To account for this mathematically, we use something called the arc length because the length here is going to be longer than just the horizontal length because it does curve. The arc length is a formal way of calculating the length of a curved object. The idea is to approximate the curve by straight line segments because it's easy to calculate the distance between 2 points by a straight line, but the curve is harder. Then we allow the approximations to get better and better by taking more and more line segments and allowing them to get smaller and smaller. And finally, we take a limit as the number of line segments goes to infinity. The integral is a symbol that's used in calculus to help encapsulate this idea of taking better and better approximations and then a limit as the approximations divisions go to infinity or as it becomes more perfect. This is extremely useful in a wide number of applications, and it applies not only in this arc length area, but to all kinds of mathematical formula and things that are derived using integration. To eliminate what a difference taking arc length into account makes, consider these 2 calculations. The arc length from an X value of -3 to -2.5 is 1.245485 approximately, whereas the arc length from -0.5 to 0, or in the middle of the ellipse instead of along the end, is only 0.50104432 approximately. So towards the end of the ellipse, the length of the curve is much, much longer. And this means that by just dividing the rows using the horizontal length, we are neglecting how the fabric curve will then impact, again, the way that it is curving. Therefore, we changed our model to not only take into account the crocheter's gauge, but determine where new rows should be created based on the arc length instead of horizontal X units. This allows us to affect the shape of the fabric more accurately, even as the fabric itself is curving. So for example, here, if you look at the rows and the circumference based on 1/2 a distance, we have these circumferences. The end rows are supposed to cover more distance than the middle though. And just as another point to emphasize, rather than dividing equally in the X direction to get rows, the total length across the X direction was 3 and 3, so 6. But if you measure the arc length across the whole top of the arc of the ellipse, you actually get 8 units approximately, which means just by our crude division into 2 rows for each unit in the X direction, we're missing at least 4 rows based on the arc length, but definitely even more. So to simplify, we're going to let 1 unit equal 0.5 inches. So 1 row is about 0.23 units. And now creating a pattern based on splitting in the X direction, but based on an arc length instead of just horizontal length, we actually get many more rows, and you can see the stitches are more roundly distributed, particularly towards the end, so it will create a more attractive and more accurate shape. What about the other surfaces? Most of them can be obtained using the same exact techniques as before. If you look at them, many of them just consist of circles. In fact, I'm going to stop sharing my screen for a moment to show you some models here. So here is a hyperboloid of 1 sheet that I created, made out of circles. Here are a couple of paraboloids that I created, just consisting of circles going round. Here's a hyperboloid of 2 sheets joined by some wire. It's actually made out of this really cool, like almost velvety yarn. It's very interesting with purple and blue colors. Here's actually a very sad looking ellipsoid from before we started taking arc length into account. And so we can get all of these, share my screen again with my slides, almost all of these quadric surfaces from using the same kind of techniques, taking into account gauge and using arc length to help determine the number of rows and circumference, as well as gauge and scale to determine the number of stitches in each row. While we were creating these patterns, because we were using this algorithm with circles and arc length over and over, I suggested that we create a program to do it for us. Megan was skeptical, but she has done quite a bit of programming. And within a month, she texted me saying, "Look what I made." So what does this program do? The input is a function and some bounds. The function is just a curve that will be rotated around the x-axis or the horizontal axis to create a surface. It also takes into account gauge measurements in scale, or how many inches per unit, and it will output a crochet pattern using just those 3 stitches that we discussed: the single crochet decrease, and single crochet increase, to model the surface that results from rotating the curve about an axis. Now, the question is, does the program do what we want it to, and how far can we push it? The program does work nicely for many functions. In fact, I have some other models here that I made based off of it when I was troubleshooting the program. So I'll pause my share. Can you guys see me better now? Can you all see me better?
People can see you better if they can go to speaker view.
Ah, okay. All right.
Perhaps they can't. If you go to gallery, then not sure. Marty?
Amanda, sorry, were you thinking you were closing your screen share?
Yeah, I just paused it.
Okay, pausing doesn't actually close it. So if you want to close it, you have to stop share.
Oh, okay. So I'll stop sharing. Thank you, Mari. So I'll hold up some more models. This is a model that was created by taking a sine function, which has a wavy look and rotating, or actually the absolute value of a sine function and rotating. This is a model that I created from a pattern output by the program, which looked kind of bow-like, but had this very big increase after the dip in the bowl structure. And you can see how the fabric is folding over itself because there's so many extra stitches from increases here. And what I found was that there were some problems in the program, and Megan had also discovered these as well. So these are things that we are working on. I'm going to share my screen again, and I'll have to start the presenter view. Play from current slide. So it does achieve nice results, but it works on a limited degree of functions. Our program, again, only allows you to single crochet increase in one or decrease one in each row. But there are functions that increase or decrease too quickly and don't work with the program. So the question is, are there functions, gauges, and scales for which it may be necessary to allow more than a single crochet increase or decrease, and instead need to crochet like 3 stitches in one or crochet 3 together? How much is enough? Like, how far should we push this? Or based on having a single crochet increase and decrease, in every row, we can double the number of stitches or halve the number of stitches. And is that enough? For example, can we care for some of these problems by taking into account the gauge and the scale alone? So here's an example of something that, of an output from the program. It's at the function x cubed plus 2x squared minus 2x plus 4, with the x bounds or horizontal bounds being from -3 to 1.25, scale of 4 stitches per 4 inches. And you can see that it actually says SC stands for single crochet. So you put 6 stitches or 6 loops on your crochet hook or ready on a chain, and then you single crochet -1. So this is a big indication that there's a problem and the program cannot output what we want here. But again, how much is enough? Okay, so a fun exploration for those more mathematically inclined is doubling the stitches enough, or can we deal with scale or something else to help? So here's something that one can look at. If we have a slope of line M, and if the circumference of the surface at a certain point is 2 pi r, how much is the circumference 1 away? And if you analyze this based on the slope and what we know, you should get that the radius increases by exactly this amount based on the slope. You may have to write some things down to see that. So it's a good exercise. But what this means is that row to row, the number of stitches should change by at most the limit as m approaches infinity of the scale times the stitch gauge times 2 pi m over the square root of 1 plus m squared. And this limit as m approaches infinity, this last part just approaches 2 pi. So we get 2 pi times the scale times the stitch gauge. So this is part of an exploration. Of course, we can generalize our program in many different ways and take different things into account. But what are some next steps? We'd like to smooth the program to deal with more pathological examples that do increase or decrease very quickly, as well as symmetrize about important features of the graph, because right now to reduce propagated error of taking arc length in different spaces, I actually, and Megan as well, had as a part of our algorithm, I had suggested that we look at the accumulated arc length and look for integer numbers related to the scale and the gauge, so that we don't have more and more variance from rounding over and over. But you know, if you look closely, you don't even have to look this closely at this small model, you can see there's some issues of symmetry that come from the approximations, and partly that it's just such a small model. So symmetrizing around important features such as maximum or minimums of graphs in terms of the approximations could result in more beautiful models. Another interesting direction to take this is the Pringle or saddle is one of the quadric surfaces, and it is unlike the others because it's not just made from circles. We had to make a very different pattern for this particular quadric surface. And so can we generalize that with saddles with different formulas and extend to bumpier surfaces that include as a part of the surface a saddle? So then the question is also, how can we make our models more beautiful? So we ultimately want to make these structures look very, very attractive as well. So things like, how can materials and scale impact the results from the patterns that we're getting beyond the soft materials we've used to create small scale models? What will be beautiful on a large scale? Will the soft yarn sculptures take on an organic form that adds to the beauty of the resulting pieces? And how does that contrast with the use of hard materials like crocheting with wire, which is something I've experimented with, or knitting with wire, or dipping pieces in glue to harden into a wicker-like surface? That's actually something I've done with knitting. I made a lamp out of yarn that I dipped in glue and allowed to harden. There's also issues of materials which relate to scale and gauge. For example, the piece that I showed you that is kind of bowl-like, that increases quickly near the ends, didn't rebound as quickly as I'd like based on the curve that I had used, in part due to the small hook size that I used and made the material thicker and therefore stiffer and less likely to curve in the way that I want. So the physics of the material themselves, as well as the gauge and stitch size and everything, all come into play. Finally, I would like to recognize Ruth Asawa, who is a Japanese artist who passed away, Japanese American artist. She was born in California, who passed away in 2013. I discovered her work when searching for structures crocheted using wire, because I was curious about the aesthetics when hardening these soft yarn sculptures. Her sculptures are beautiful and illustrate mathematical forms that are, many of them are surfaces of revolution. And they also still have yet an organic or soft feel, even though they're sculpted in wire through crocheting. Although she did not approach these sculptures in the same mindset as Megan and I, she was a visionary and remains an inspiration as I experiment with soft calculus and creating beautiful structures from it. Thank you.
Thank you, Amanda. Okay, do we have any questions, comments, observations? Amanda, one question that I had was, is in the field of mathematical education, is it are people pretty familiar with the possibility of using crocheting as a kind of educational tool? I mean, do you see articles about it and things like that?
Yes and no. So I would say in terms of geometry, a lot of people will use programming to help visualize, and as well in Calculus 3 courses. But I had never really seen to this extent people using crochet models, except in terms of hyperbolic models. There are more and more people exploring mathematics and art research related to crochet and knit, however. And there are people interested in the physics of different knit stitches. For example, there is a researcher at Princeton University now who she's pioneered that work. Does that answer your question? So I would say to a limited extent.
Good. Hope has a question in the chat. Perhaps you already explained this, but is knitting equally as useful for these kinds of models, or is crochet a superior technique? If so, why? Also, are any of these techniques being used in the other direction towards, for instance, garment or other production?
Ah, interesting. So the reason that I chose crochet, I actually prefer knitting, if I'm going to be completely honest. But the reason I chose crochet is because the models that I was looking at making were primarily made from circles. When you're making small knitted models in a circle, you have to use what are called double pointed needles. And it looks like this crazy contraption of needles for those who don't know. And there are all these loops. And if one of your needles slides out, you have all these loose loops that can then unweave and create disaster. So it's definitely intimidating for those who haven't done it. Whereas with crochet, you focus on one loop at a time, and you only have one loop from which things can unravel. So from an educational perspective, I thought if someone has never done this before, it's much more approachable to start with crochet. I personally like the fabric created more from knitting, but both can be used. But the reason I chose crochet is just if someone has never done it before, it's still hard. I've learned this from running workshops. It's still really hard to learn, but not as bad. I have been fantasizing about creating fashion pieces based on this. As far as I'm aware, I wouldn't be surprised if someone has approached from these kinds of perspectives, but I'm not aware precisely of anyone doing so. 3D printing could definitely be used as well to answer Lyle and Beth Slack's question to create these things. Although I think the approaches are different because the technology is quite different, whereas we're building just from the ground up programming that outputs patterns.
Okay, more questions. Last chance of the year to ask a question at the Berggren Forum and get extra credit for participation.
A hyperbolic coat, oh my gosh, Hope, that would take a lot of time. You know, when I read about Dinah Tamina in Science Magazine when I was an undergraduate, it mentioned that she showed up to the interview with a hyperbolic skirt. And I actually wrote to her and I said, how did you create your hyperbolic skirt? And I thought I would get something more than the standard answer. I was naive to think I would even get an answer probably, but she did answer. She responded to me and she said, chain as many stitches as you need for your waist size, and then just create a hyperbolic plane. Be patient, it takes a lot of time. For instance, the Lorenz manifold that I displayed earlier, the wavy white and blue shape took 85 hours of time to create So when you have a lot of fabric, you're cramming into a small space that's all windy. It takes an enormous amount of time, but I would love to see a hyperbolic coat as well. That would be beautiful. I believe Elizabeth Matson, since I mentioned the idea of a hyperbolic skirt to her, she has started making one. So maybe we will see one of those from Dr. Matson at some point. And I see a question from Lakeen Simon Romero as well. What about basket weaved quadrics? I love that idea. I've actually been researching about weaving recently. And there are some beautiful YouTube tutorials which explain how to weave with small pieces as simple as pine needles from your yard. It takes a lot of time, but I think that's a wonderful idea because it can provide you with a surface that is malleable, but will hold a shape better and therefore communicate the form you're trying to better.
Any more questions people have for Amanda? Amanda, I was discouraged when you just said crocheting is hard. I mean, isn't crocheting something very, very simple, not too difficult? I've never crocheted anything.
Well, it's kind of like learning to ride a bike in the sense that it's very hard at first, but once you get into the rhythm, it's almost something you can never forget. And the same thing with knitting. So once you get the mechanics of the fine motor skills down, it's easy and very relaxing and meditative, but it is kind of stressful at first because there's kind of a lot of little things you're doing with your hand and in terms of the weight that you have to get used to. And I'll be honest, it surprised me a little bit. I realized how experienced of a knitter and crocheter I had become when I ran the workshop that I did a couple years ago and saw how frustrating and hard it is for people who had never seen it. Of course, I'll get better at teaching it as well with time, but I do believe it's one of those skills where, like riding a bike, it's quite difficult at first, but once you get the mechanics down, it's fun and relaxing and something you don't forget. Hi, Lenny. Kat making a brief announcement.
Well, I mean, one of the things, this Bergman Forum is perfect because it gives Gary Ostrower a retirement project, doesn't it? Take up crocheting.
I would love to have more people to work with on this too. It would be very fun. Thank you, Lakeen.
Okay, any more questions? If not, I'll thank Amanda. I'll thank Mari again for her help today and the time. Thank you all for participating, and see you all in January.